Hello everyone, I'm Greg Karlovitz from the Hydrologic Engineering Center. Welcome to our course on statistical methods in hydrology. This video is part 3 of 3 on the topic of precipitation frequency analysis, and we'll discuss storm typing. Let's get started. Storm typing is an effort to divide the precipitation record by the meteorological cause. It's where meteorology meets statistics. Storm typing is considered a recent advance in precipitation frequency analysis. Each day of the record is divided into a number of meteorological themes that explain the atmospheric conditions that generated the rainfall. The idea is that storms of the same theme are more likely to have similar statistics than storms of other themes, even if they're both annual maxima. The frequency analysis is then performed individually on each of the themes, called storm types, by extracting a partial duration or an annual maximum series for each type of storm. These samples are more likely to be homogeneous and conform better to traditional extreme value analysis. We will very briefly delve into an extremely high-level overview of the relevant meteorology here. In North America, we typically use 4 broad meteorological themes as our storm types. These are the mid-latitude cyclone, tropical storm and tropical storm remnants, mesoscale storm with embedded convection, and local storms. These vary by spatial and temporal scale, the source of moisture, and the type of uplift. There are 2 types of synoptic scale storms. MLCs are non-tropical source cyclones, sometimes called extratropical cyclones. They share a lot of properties with TSRs, but do not get their moisture from the tropics. They're the largest spatially and temporally, covering over 1,000 kilometers at a time, and affecting a given location the most over a 48 to 72-hour window. The storm itself will remain organized and last longer than that overall, but it's likely to rain the hardest at a single location over about a 48 to 72-hour window. Frontal precipitation is associated with cyclones. MECs are smaller in scale and duration, but may still be fiercely intense. They belong to the mesoscale classification of meteorological events, with a typical scale from 5 to 1,000 kilometers. They're typically well-organized convective systems, such as mesoscale convective complexes, that have a complex spatial pattern of precipitation with cells that can be very intense locally. The typical analysis duration for these kinds of storms is 6 hours, although a mesoscale convective system can be longer lived than that. They're typically very fast-moving, so the rainfall at any location can be very brief but very intense. Finally, local storms represent locally intense precipitation such as supercell thunderstorms. They're usually very short-lived and typically do not contribute to the record of the most extreme events. They are analyzed using a 2-hour duration. Storm typing has 2 benefits for the precipitation frequency analysis itself and 1 major benefit for the application of the findings. First, when regionalizing by storm type, the analysis can consider a wider regional basis as long as the predominant storm types exist in those places. This helps draw on even more data when building the regional analysis. Ordinarily, in a normal precipitation frequency analysis, the data are drawn from annual maxima regardless of storm type. When the dominant storm type changes, so does the makeup of the annual maximum series. By considering homogeneous storm types, this variation goes away. The homogenization has the effect of decreasing the prevalence of mixed populations. By looking at the annual maximum series by type, we know that the same causal mechanism is in play, and the samples are more likely to be drawn from the same population. Homogeneous time series also tend to work better with a classical extreme value analysis, with a result that gains strength from having that foundation. Finally, when applying the data, the frequency estimates can be combined with spatial and temporal patterns and depth area reductions that are appropriate for the type of storm being modeled, instead of mixing and matching frequency-intensity relationships with spatial and temporal patterns. There is a downside to this, as there's no such thing as a free lunch. Storm typing is a labor and resource-intensive procedure that requires a great deal of expertise to perform successfully. We've also learned that there really aren't any shortcuts worth taking when trying to do it either. This is an example of 48-hour 1 in 100 AEP isopluvials for MLCs on the left and TSRs on the right for the Tennessee Valley, courtesy of MGS Engineering and the Tennessee Valley Authority. The results show how the depths and the spatial behavior for these 2 storm types vary from each other in a meaningful way. For example, TSRs experience a certain amount of shielding due to the mountains in the eastern part of the study area that MLCs do not experience. There's an important connection to extreme value theory from this storm typing discussion. When we make sure our populations are homogeneous and not mixed, their properties can more reliably be predicted by extreme value theory. This aids us in choosing the right probability distribution for these extremes. Why is selecting the right model so important? The graph on the right shows the contribution to uncertainty at varying AEPs for a study area. At the extremes, the choice of distribution and its associated uncertainty becomes the largest source of uncertainty in the analysis. When we're using these kinds of analyses for investment decisions about things like dam safety, reducing the substantial uncertainty at the end of the curve that affects the decision the most is valuable. In this video, we discussed storm typing. The key point to take away from this video is storm typing can enhance a precipitation frequency analysis by producing homogeneous samples with excellent modeling properties. However, storm typing requires a lot of extra effort. Thanks, and come back soon to learn about other topics in our statistical methods and hydrology course.